There is no place in the universe that is truly empty, but the space between clusters of galaxies comes close. These regions contain less than one atom in every 10 cubic meters, or 350 cubic feet, or only 3 atoms in a space about the size of a small room. Although galaxies continually supply new material to intergalactic space, the continuous expansion of the universe makes the net effect nil. Intergalactic space is very empty, and it is getting emptier as the universe expands. The more we learn about it, the more complicated the expansion of the universe seems to be. In the region near our galaxy, the expansion seems less rapid than for the universe as a whole. In fact, it appears that the combined gravitational pull of a very large cluster of galaxies in the constellation Virgo is actually retarding the local rate of expansion to half the rate for the universe as a whole. We are finding evidence of how gravity attracts even over distances of hundreds of millions of light years. Although there must be many very distant galaxies and quasars that we are not yet able to detect, astronomers have observed radiation from an even more remote source, literally at the edge of the observable universe. As we look far out in space, we are looking back in time, since light waves take time to cross space from their source to the observer. Hence, we view distant regions of the universe as they were long ago. According to the Big Bang Theory, the universe originated in a great explosion and has been expanding ever since. At a very early epoch, before galaxies and stars formed, the universe was filled with hot glowing gas, and it was opaque. At some point during the first million or so years after the Big Bang occurred, the expanding and cooling gas became transparent. Hence, we can see out into space and back in time only until we come to the distant region that we observe as it was in the era when the universe cleared. Before that point, space is opaque, so light waves cannot reach us. Astronomers have used the James Webb Space Telescope to peer back in time to early days of the universe, and they spotted something unexpected. The Space Observatory revealed 6 massive galaxies that existed between 500 million and 700 million years after the Big Bang that created the universe. The discovery is completely upending existing theories about the origins of galaxies, according to a new study published Wednesday in the journal Nature. These objects are way more massive than anyone expected, said study co-author Joel Leha, assistant professor of astronomy and astrophysics at Penn State University. In a statement, "We expected only to find tiny young baby galaxies at this point in time, but we've discovered galaxies as mature as our own in what was previously understood to be the dawn of the universe." To detect faint infrared light, the instruments inside the telescope have to be kept very cold. Otherwise, those infrared signals could get lost in the heat of the telescope. The spacecraft's orbit and tennis court-sized sunshield keep light and heat from the sun, earth, and moon from warming up its sensitive instruments. And the MIRI instrument, which needs to be even colder to capture mid-infrared wavelengths, is equipped with a special cryo-cooler. The unique design and innovative techniques used by the James Webb Space Telescope are what made the first images possible. As the mission continues, more targets will be observed, more discoveries will be made, and more of our universe will unfold before our eyes. It's not every day you can say you contributed to something that inspires the world in a positive way, but I believe that's what JWST is doing for everyone of all ages, said JPL engineer Annalyn Schneider, who is the project manager for the telescope's MIRI instrument. The telescope will help us learn more about our galaxy and the rest of the universe, and as a bonus, we get these magnificent images. Learning is a big part of being in science and engineering, and that's what makes it interesting and challenging. The telescope observes the universe in infrared light, which is invisible to the human eye, and is capable of detecting the faint light from ancient stars and galaxies. By peering into the distant universe, the observatory can essentially see back in time to about 13.5 billion years ago. Scientists have determined the universe is about 13.7 billion years old. The revelation that massive galaxy formation began extremely early in the history of the universe upends what many of us had thought was settled science. Le has said, "We've been informally calling these objects universe breakers, and they have been living up to their names so far." The galaxies are so massive that they conflict with 99% of models representing early galaxies in the universe, which means scientists need to rethink how galaxies formed and evolved. The current theory suggests galaxies began as small clouds of stars and dust that grew over time. "We looked into the very early universe for the first time and had no idea what we were going to find," Le has said. "It turns out we found something so unexpected it actually creates problems for science." It calls the whole picture of early galaxy formation into question. Additionally, two planets about as massive as Earth orbit a red dwarf star only 16 light-years away, nearby in astronomical terms. The planets GJ1002b and C lie within the star's habitable zone, the orbital distance that could allow liquid water to form on the planet's surface if it has the right kind of atmosphere. Whether red dwarf stars are likely to host habitable worlds is a subject of scientific debate. On the minus side, these stars, smaller, cooler, but far longer lived than stars like our Sun, tend to flare frequently in their youth. Such flares could potentially strip the atmospheres from closely orbiting planets, and the two planets orbiting GJ1002 are close indeed. Planet B, with a mass slightly higher than Earth's, is the closest of the two. Its year once around the star lasts only 10 days. Planet C, about a third massive than Earth, takes about 20 days to orbit the star. On the plus side, however, GJ1002 seems to be mature enough to have gotten over its youthful tantrums and now appears quiet. It's even possible that the early flaring helped build up a variety of molecules on the planet's surfaces that could be used later, during the star's quiet period, by any developing life forms that might be present. An international team led by Alejandro Suarez Mascareño of the University of La Laguna, Spain, discovered the two new planets using radial velocity measurements, that is, detecting the wobbles of the parent star caused by gravitational tugs from orbiting planets. As the planets move toward the far side of the star, they pull the star away from us, causing the star's light to shift toward the red end of the spectrum. As the planets move towards the star's near side, they pull the star in our direction, shifting its light toward the blue. The planetary tugs on GJ1002 are tiny, about 4.3 feet or 1.3 meters per second, equivalent to moving to about 3 miles per hour or 4.8 kilometers per hour. Such small movements are difficult to detect. The radial velocity method, which also reveals how massive the planets are, have yielded more than 1,000 confirmed detections of exoplanets. The most detections, however, have been notched using the transit method, watching for a tiny dip in the starlight as the planet crosses in front of its star, with nearly 4,000 confirmed detections. To make its radial velocity measurements, the science team relied on instruments called spectrographs, which measure variations in light. The spectrographs used to discover GJ1002b and C were part of two collaborative observation programs: the Echelle spectrograph for rocky exoplanets and stable spectroscopic observations, or ESPRESSO, and the Kalar Alto high-resolution search for M-dwarfs and exo-Earths with near-infrared and optical Echelle spectrographs, or CARMINES. The newly discovered planets join 10 others in a fairly exclusive category: small worlds in the conservative habitable zone that are less than 1.5 times the size of Earth or less than 5 times as massive. If we loosen the membership criteria a bit, that is, if we include slightly larger planets in the optimistic habitable zone, the group expands to about 40 exoplanets, or planets beyond our solar system. The conservative habitable zone is a stricter boundary for the region around the star that might allow planets to harbor water. Optimistic habitable zones expand that boundary a bit. Any habitable zone estimate is a rough approximation. So far, none of these worlds' atmospheres have been fully analyzed, and many might not possess atmospheres at all.